G'day everyone, welcome to Lubrication Explained. In this video, we're going to talk about all the things that you need to know to get started with a used oil analysis program. So all the things which are really important to your organization and things that you want to set up well at the beginning to set you up for success. Alright, so why do we do used oil analysis in the first place? Well, something you may not know, but something I have mentioned on this channel before, is that 23% of all of the world's energy consumption comes from what we call tribological contacts. So effectively that's frictional contacts. Of that, about 3% goes just into remanufacturing worn parts and manufacturing spare equipment due to wear and wear related failures. So that's where lubrication really comes into its own and can have a huge impact on, our society, energy consumption, and your maintenance program. We can drastically reduce energy losses due to friction and wear, and that's really going to help us in the long term. Now you've got to remember, if you look at this data, it says that 1.4% of global GDP could be averted just by some simple measures. Now 1.4% takes into account a whole bunch of sectors over which lubricants have no relevance. So things like the IT sector, the service sector, hotels, hospitality, tourism, all that kind of stuff. So you've got to carve all of that out. So in the businesses that we're talking about, industry, transport, personal vehicles, that 1.4% number is going to be significantly larger. It's going to be closer to sort of 5, 6, 7%. And as a proportion of your maintenance budget, it's going to be even higher still. So this is showing kind of the importance of getting lubricants and lubrication correct. Now all of this comes from a 2017 paper in the journal called Friction. So I want to acknowledge the authors for some of the great work that they did there. Okay, so why do oil analysis? Well, I always like to give the analogy of going to a doctor. So you would go to the doctor for a standard checkup. Okay, they'll probably take a blood sample, and that blood sample can help you to understand the condition of your body. Hopefully, you want to detect conditions and diseases before they really get to the point where they're serious. That's kind of the aim of a regular checkup. Now, in-service oil analysis is very similar, in so much as a single test can be useful, but not as useful as if you were to put it into context. So let's say you took blood samples every 6 months for 10 years. Over that long period of time, you would be able to see things like, what is my blood cholesterol doing, as an example. So if bad cholesterol is gradually creeping up, then your doctor may make a recommendation to intervene, change something about your diet or exercise program, and that way you can start reducing your cholesterol before you have a heart attack, right? Used oil analysis is exactly the same thing. We want to intervene early so that we're intervening before a catastrophic equipment failure. Now, used oil analysis is not a panacea, right? It's not the cure-all. It really needs to form just one part of an effective preventative maintenance program. So when we talk about that kind of stuff, what are the benefits? So we can maximize our oil drain periods. We can determine suitability for continued use. So that's, is the lubricant fit for continued service? We can evaluate equipment condition. So is my equipment operating in the way that I would expect? And we can also do some troubleshooting. So that can be both in real time and post a failure event. We can use used oil analysis data as part of our investigation. Alright, so what are the keys to an effective used oil analysis program? I like to put them in 5 buckets. First of all, you need excellent sampling technique and information input. So this goes to the field personnel who are actually taking the samples. Sample hygiene is just incredibly important, and we will talk about that. The testing accuracy and the consistency. So this is really down to lab selection. Are they ISO credited, for example? Are they doing regular spot checks? Understanding lubricant chemistry and action. At the moment, for the most part, it's the lubricant majors who understand lubricant chemistry. Unfortunately, out there in industry, we have some great machinery engineers who might understand the inner workings of, the latest gas turbines, but very little understanding of the actual lubricants that they're putting into that gas turbine. We need to overlay that with some modern data analytics and machine learning tools, just to get the maximum value out of our data. And finally, we need to connect that data to the application. So, machine learning tools are only good if we can interpret them correctly. So this is kind of a bit of a framework. These 5 keys, I'm going to flash them up on screen where they're relevant, so we can see, where it is going to get the maximum value for our organization. Okay, so let's get into the how to do oil analysis. So when you're taking a sample, it's important to know that the laboratory is going to be looking for particles that are less than 8 micron. How big is 8 micron? Not very big at all. Okay, so human hair is about 75 microns wide. A white blood cell is in the order of about 25 microns. 8 micron, to give you an idea, is not visible to the naked human eye. Right, so even though a sample bottle might look clean, it's really important to flush new oil bottles because it is entirely possible that they have been contaminated. If you're doing particle analysis of a very crucial bit of equipment, let's say it's a hydraulic pack with very tight tolerance servo valves, then in that instance, you would probably want to flush the bottle a couple of times to ensure that it has not been contaminated. We also want to clear around the actual sampling point as well, because we don't want that to contaminate the sample. If at all possible, we want to avoid sampling from the drain plug. Now, the reason for this is because, in the sump, that's where, it's a low flow area and it's probably the coldest part of your equipment. And so all of the, used additive, contaminants, machining swarf, all of that kind of stuff ends up at the bottom. So if you were to take a sample from there, what's going to happen is that all of that crud ends up in your sample bottle. Okay, and that's going to contaminate the sample and cause the results to not be representative. All right, next thing that we need to do is inspect the sample. So here, it's crucial that the person taking the sample understands what is normal, right? They are the first line of defense. So a sample needs to have sufficient volume, it needs to be clear and free of sediment. And the reason for that is because sediment can damage equipment in the used oil analysis lab. So if they see free sediment, they probably won't do the full test slate of tests. If you have darkened or discolored oil, that could be a sign of something. It could be soot loading, oxidized oil, or it could be perfectly normal. Some oil does go dark in service. So again, whoever is taking these samples regularly, if the oil always looks dark, that could be perfectly normal. Okay, sediment could be a sign of either oil contamination or sample contamination. But if it's magnetic, that could also indicate that it's rust or possibly even very severe wear. You'll see that show up on the PQ index. Free water, that's obviously a sign of water contamination. Free water is generally a bad sign. You'll probably be aware that water will generally sink to the bottom because it has a higher specific gravity than lubricants or oils. However, there is an exception in that polyalkylene glycols have a higher specific gravity than water, and so the water will actually sit on top. That's really important to know as well, because that means in those applications you can't just open the drain plug and drain water out, because it will sit on top. All right, so how much water is normal, and how can you tell? So if there's haze or there's cloudiness, that could be an indication of water, wax, coolant, or refrigerant, right? Could be any of those. As a general rule of thumb, we say that you should be able to read a newspaper from behind the sample. Okay, that's an acceptable level of water contamination. Then we've got to log and send the sample. So we need to assign the bottle to an asset, right? That could be a barcode, it could be a QR code for some of the more modern used oil analysis programs. But either way, you need to assign the bottle to the asset. And then you want to document as much information as possible. So, what date was the sample taken? How many hours has the machine or the oil got on it? Maybe how many kilometers has the vehicle driven? Have you changed the oil before or after the sample? Have the filters been changed? These are all relevant data points that are really going to help when we do trend analysis. Also, make sure you use the mailing container, because that will ensure integrity all the way to the lab, and mail your sample. I cannot tell you the number of times that I've been questioned about where a sample might be, and as it turns out, it's just sitting on someone's desk. All right, so then we get into the question, when do we want to do an oil analysis? And the when of the question, we need to backtrack a little bit and talk about sort of a foundational concept in maintenance engineering, which is the P to F interval. And what that says is, for every failure, right, we can track backwards in time, and there will have been the onset of a problem. So as an example, I use the example of a bearing failure. If the bearing failed catastrophically, it started with some kind of event in the past. Maybe it was that when the bearing was installed, it was installed with a slight misalignment. Maybe it's actually the wrong bearing size or wrong bearing fit. Maybe there was some contaminants that were introduced into the bearing. Whatever it was, the problem started a very long time ago, and it didn't manifest itself for a while. Now, all the different tools that we have in a maintenance and a preventative maintenance program are designed to try and pick up this problem before it results in a failure. So you'll be able to see things like a change in the vibration signature. You might start to see wear debris in the oil. Infrared thermography might be able to pick a change in temperature. Then when it gets really bad, you'll walk past the machinery and you'll notice that the noise it makes is different. Eventually, when it gets really severe, it'll get hot to the touch, and then you get failure. So where does used oil analysis fit in? Well, obviously we can look at wear debris in the oil, right? That's one of the things that we can kind of assist with. And so it's really important to understand this concept and to know that with reliability engineering best practices, we want to be scheduling our diagnostics at no more than half this P to F interval. The thing about the P to F interval is that it's not constant, right? So if I were to have, let's say for example, a bearing that was installed with a very, very minor misalignment, maybe the time to failure is 12 months, 18 months, something like that. Whereas if it was the wrong bearing that was installed, maybe it only takes a week before that thing absolutely dies. So there's kind of a distribution of time to failures, right? And with that distribution, what we can say is that the sampling frequency will help us to pick up on a certain percentage of those failure modes, right? So theoretically, if the sampling frequency, let's say my mean P to F interval is 3 months, so about 90 days. If I sample every 90 days, I should be able to pick up half of those issues. And as I increase the sampling frequency, I increase the proportion of failure modes that I can pick up before it fails. So here we're talking about sampling technique and information input. So the sampling frequency is what's really critical. Now, it's very difficult, obviously, to quantify that. So generally, there are some guidelines. I picked these ones up off the mobile website. where they talk about how frequently you should be sampling, right? And for different applications, there are some general guidelines. All right, so then we've sampled, we send it off to the lab, and we get our report back. And we want to kind of talk about all the different elements on the report. What do we need to look out for? All right, so the first is sample information. Okay, this is user input. So you put this in. And we want to make sure that all the information is there. Different people have probably been taking these samples over the course of months or years, and maybe their tolerance for how much information is required may differ. This is where we want to strongly advise people as much as possible. Put all the information in. Often you won't get another chance to do it. All right, so the next step, there'll be a section on lubricant properties. These are things like oxidation, right? So how much has the oil degraded in service? TBN and TAN, right? So the acid number and the base number. The bulk viscosity, either at 40 or 100 degrees. These are all kind of information about the lubricant, and we need to, in order to interpret that, we need an understanding of basic lubricant chemistry, right? So when we talk about oxidation, what is that? So the next part that we might want to read is the wear metals. And wear metals as a standalone information source aren't all that useful. Where it is useful is where we can connect that information back to the application, right? So if I have aluminium increasing, well, I need to know where the aluminium is in my equipment, right? So if this were the report for an engine, for example, does my engine have aluminium pistons? If so, well, that's likely to be the wear source, right? That might be something that warrants further investigation. All right, so the next section is contaminants. Again, we want to try and relate this back to the application. So if it flags as a coolant leak, is that possible? Do I have coolant around my application? If silicon and aluminium show up, often that's actually a sign of dirt ingress. So where could those contaminants have come from? The next part is the additives. So again, unless we have an understanding of lubricant chemistry, the additives section isn't all that helpful for us, right? If I don't know what calcium does in a lubricant, what use is it to me to know the level of calcium? Now, as happens with engine oils, generally calcium is related to the detergent additives, so that basically it's related to the TBN. But again, I have to know that to be able to make use of that information. You'll also see some kind of graphical representation of the recent asset history, and I'll describe in future slides why that can be a little bit dangerous. But the final part of the report will be an overall report status. So generally it will be on kind of a traffic light system, which is green means normal, yellow is caution, and red means alert. Something is out of the ordinary and you need to go and look at it. Now, the thing about this traffic light system is it is based on very rudimentary machine learning tools, right? So based on your used oil analysis results, it is most likely that the used oil analysis provider is automatically selecting a traffic light condition. So there's probably no human input here. But it's doing it at a very basic level. So the computer just has set limits, maybe for the application, and says, oxidation above 20 means red, right? So again, it's not telling you anything in context. It's up to you to do the interpretation. So as an example, how would we use elemental analysis? Like I said before, it's important to know where does the element come from. So this is all about connecting data to the application. So if I have an engine, where could iron come from? Where could lead come from? Where could silver come from? If you see it in your used oil analysis results. So let's take a real world example. If I have an engine oil, if I were to have just a single used oil analysis result, and I saw really high copper, what does that actually mean, right? Copper can come from a few sources in an engine. Potentially it could be the bearings, right? Big end bearings or small end bearings commonly have copper in them, but there are also copper oil coolers, also very common, right? So trying to figure out where the copper comes from, that requires a little bit more analysis. So all I can know from this result is that the copper looks elevated and everything else looks normal. So let's try and do some trending, right? Now, this is probably what it would look like on the used oil analysis report, and this trend looks linear, right? So the copper is just increasing in a linear fashion. However, this can be a little bit misleading, because if you look at the x-axis is assuming that all of the samples were taken at regular intervals. Now, what if they weren't taken at regular intervals? This is an example where now, with the same copper results, right, but now I've plotted it versus, let's say, engine hours or something, now we're seeing an accelerating pattern. Now, this is very typical of wear, right? So this would then point you towards the bearings, saying, maybe I should check the big or small end bearings if that's possible. All right, so let's go back again. And instead, what if it were the same copper values, but on the engine hour trend it looked like this? This is a decelerating pattern that looks much more typical of something like copper passivation. Now, before I jump and make a conclusion that, oh, this is just the coolers, I don't have to be concerned about my bearings, I want some way of validating that. So now I have to understand how the lubricant works with my copper coolers. So I've shown this diagram a little bit before, where you've got copper on one side and you've got the metal deactivators on the other side. So copper is going to want to kind of bleed in, I know that's not the technical term, but bleed into the lubricant, right? And the additives are going to want to, because they're polar, bind to the surface of the metal to basically take up all those corrosion sites. And so as this continues on, you can see that the surface area that's available for the reaction to happen gets smaller and smaller and smaller. And that's why we see a decelerating pattern. Right, so now that I have that understanding, I can actually get the lab to confirm what kind of copper is in the sample. So if I have what we might call copper wear, I should have particles in the sample. And if I were to spin that sample through the centrifuge, all of those copper particles should end up at the bottom of the sample. So now if I were to retest and do the ICP analysis again, I should see lower levels of copper, right? If it were as a result of passivation, I would expect the copper to be in kind of like ionic form, so it's in solution. And that would mean that centrifuging wouldn't do anything to it. So in the real world, what we do is we centrifuge the sample and then we test it again, and lo and behold, okay, the copper hasn't really dropped all that much, right? So that suggests it's passivating oil coolers rather than bearing wear. The other thing which you'll notice on this particular sample is that the iron did drop, right? So iron went from 11 to 0, and that's because the iron is probably wear metals as opposed to, iron in solution. All right, so conclusion and challenges. So going back to the keys to an effective used oil analysis program, we said we want to have excellent sampling technique and information input. We want to have testing accuracy and consistency. We want to understand the lubricant chemistry in action. We want to apply modern data analytics and machine learning tools. And we want to connect the data to the application. Now, who is the holder of the keys in your organization? Most likely, I'm going to say it looks like this. Sampling technique is the responsibility of field personnel. Right? Testing accuracy and consistency, that's the responsibility of the laboratory. Understanding the lubricant chemistry and how it acts is probably the responsibility of your lubricant supplier. The engineer is responsible for, what was that one again? Forgot. And modern data analytics and machine learning tools, responsibility of the laboratory. Sorry, the engineer was connecting the data to the application. Right, so that's how it probably looks at the moment. Where we really want to get to, right, is a position where instead the field personnel and the engineer have a good enough understanding of lubricant chemistry that they can interpret used oil analysis results and can understand how the additives might be working in the application. And rather than allowing the laboratory to make recommendations because of used oil analysis results, we want to get to the point where the engineers can start using machine learning and data analytics to make informed decisions that really have an impact on the maintenance program. So this is kind of where we would like to get to. And this whole channel, Lubrication Explained, is about helping people to inform themselves about lubricant technology so that they can make better maintenance decisions. So in the end, right, if we put all of these things together, I firmly believe that at the intersection of all of those 5 things is where you get reliability. Right? So putting all of those things together means that your comprehensive used oil analysis program in concert with the right lubricants is going to really drastically help machine reliability. All right, I know that's been a longer video than usual, but like I said, these are all kind of the basic things that people need to get right if they want to set up a used oil analysis program. As usual, if you've got questions or comments, please leave them below. But otherwise, this has been Lubrication Explained.